Back in my day, we had a chalkboard. Okay, welcome. Let me put my cal one step away a little bit early. We still are a little bit early. Let me stall a little bit. Seeing who takes calculus 2 in your first semester at college. So I see very first semester.
Yeah.
So you did AP calculus,
Dual credit.
dual credit.
Yeah.
Good, and you were brave enough to go from your dual credit to Cal 2, because I had a whole bunch of weenies in my Cal 1 that said that they all had credit for Cal 1 and they're in there taking Cal 1 again. So what do you need me for?
Brave enough or foolish enough, we'll see.
Well, I mean,
Finally.
no, calculus 1 is kind of easy, don't you think?
It was pretty easy.
It's pretty easy. Yeah, calculus 1's pretty easy. Calculus 2 is not as easy. Some folks will tell you that Cal 2 of the 3 semesters is the hardest of the 3, but that's because you're comparing 3 kind of easy things together. I don't want you to think calculus 2 is hard. Calculus 2 is mechanical, steps. You got lots of steps to do. And you know, when things have steps, you have to do them in the right order. You have to finish that step before this step will make sense. So it's a lot of progression in calculus 2. Bit of memorizing, but if you can visualize, it's very, there's always a picture to go with the formulas. So if you're not a formula person, if you can visualize what's going on or where these formulas came from, then you're good. You've seen some formulas in calculus 1. I'm going to write them up here and see if you remember them. Where's Cassie? Cassie's supposed to be here. She's gonna be late on the first day. Geez. Okay. I sent, I think, each of you a syllabus. And we were waiting, I thought.
Can I sit right there? I didn't realize commuter west was really west.
But you've been here before.
I know, but I've never parked there. And I didn't think to.
So you're not living on campus?
Mm-mm.
Why not?
The dorms are beautiful, but
They're fine. And you can sleep later and you don't have to park.
that is true.
Okay, we were talking about the syllabus, and on the syllabus, it has my name. My name is Patty Schovanec. You say the SCH the same way you say the word school, Schovanec. I have an office in this building. It's on the 2nd floor, tucked way back in the corner. There are signs directing you to my office, so just follow the signs. On my syllabus, I gave you a phone. Don't call that phone. I don't even have it plugged in. It never rang to begin with. And students would get mad that I never answer my phone. Well, it doesn't ring, so I can't answer it. And sometimes it did ring, it would scare the bejeebers out of me. So I just unplug the thing and it collects dust. It's just an accessory. So don't call, but I have to put a phone on here. Email me. I check my email 1,000 times a day. I have office hours on Monday, Wednesday, Friday. This is my last class on Monday, Wednesday, Friday, so I'll go straight to my office. My Tuesday, Thursday is broken up a little bit more. I've got, I don't know what my schedule is tomorrow, so, but I know that I have a class in the morning. I guess it begins at 11 because I put my office hours right before my 11 o'clock class. And my class in the morning is in the Mass Comm building, which is near my home. So I'm going to do my office hours on Tuesday, Thursdays at my home. So that I don't have to walk to the math building, then walk all the way back there. And just minimize travel. So when I say virtual, you can Zoom me for those office hours. Gotta warn you though, I kind of work out during those office hours, and then when I notice somebody's on Zoom, I'll answer, so I'll look like an old lady who's been exercising. So don't worry. Then I have a class that runs till 12:30. So if I put my office hours from 12:30 to 2, then I have a 2 o'clock class. I'll often go back to my office after that class ends at 3:30. So I'm there more than what these hours suggest. So that's what the or by appointment means. If you need me at other times than that, just let me know and I'll make sure that I'm there. If you don't like in-person office hours, even when I'm in my office, if you would like to Zoom office hours, I can do that as well. And I think I put the Zoom address on here somewhere. So feel free to do it that way. The textbook is the 7th edition. You can use the 6th edition if you find one cheaper. There's very little change between the 7th and the 6th edition. And like I said, don't buy access code. We're using the free homework site, WebWork. So if they sold you an access code, take it back. You don't want it. We cover the chapters 6 through 9. Chapter 6 is a lot of the applications of the definite integral. So we're going to look at area, volume, work, arc length, stuff like that. Chapter 7 is a whole boatload of integration techniques. Right now, you know how to integrate basic integrals or basic substitutions, but there's a whole bunch you don't know how to do just yet. And that's what we do in chapter 7. So chapter 7 is techniques driven. And then in chapter 8, we get a little bit more to the abstract and we talk about sequences and series and what they can tell us about functions. And then in chapter 9, we prepare you for calculus 3. Calculus 3 is multivariable calculus. So we look in 3 dimensions and it's vector calculus. So we start talking about vectors and vector operations. Then let's see, their learning outcomes. I never read those. I just cut and paste those. We're going to teach you some calculus is what we're going to do. The method of assessment of learning outcomes is what you're interested in. I said we're going to have 3 in-class exams. Each exam is 20% of your grade. And I put those equally spaced. So I just took a Monday, Wednesday, Friday calendar and I cut it into 3 equal parts. If I have to move a test based upon where we are topics wise, I'll let you know way in advance. But right now I kind of spaced them out and I put the dates on here. Then we've got a homework grade. Your homework is homework that is graded by WebWork. So I don't take up, I give you suggested exercises out of the book so that you can improve your calculus abilities by doing these hand-picked exercises. And when I make out tests, I look at the suggested exercises. I try to make the WebWork problems reflect the suggested exercises. So I don't take the ones out of the book up. WebWork grades your homework as you submit it. And then there's another part of your homework grade called the write-ups. I want to do something a little bit more with the honors students than I do for regular calculus students. I want to see if you know how to read and write mathematics. So when I assign WebWork, in your WebWork page, in the introduction page, there'll be your WebWork assignments, and you'll click on an assignment, it'll take you to the assignment. But on that page, there's a little box over here about info. And for each WebWork assignment, I want you to take the problems that I list over here and write them up on notebook paper in a neat and organized manner with the full solutions. And then turn those in. Those are going to be called your write-up problems. You can turn them in either by bringing the paper copy to class, or if you want to just scan it and send me a PDF through email, that's fine as well. But I take the write-ups, which will be a subset of your WebWork problems. Say, suppose your WebWork consists of problems 1 through 15. I might over here say write-up problems 2, 6, and 9. And I grade them either as 0, that you didn't do a problem, One, that you did the problem and you didn't put all the steps in, or you made some mistakes somewhere. And two, that you did everything right. So each assignment is probably about 6 points of write-ups. I take all your write-ups at the end of the semester and I add them together and I get a percentage out of that. I take that as a 100-point score, and I take your web works. From your web works, I drop 2. I'll drop your 2 lowest if you'd rather me drop the lower ones and the higher ones. I'll take those web work scores, this score, add them together and average that, and that becomes your homework score. Okay, so these write-ups are not optional. The write-ups are part of your score. I don't drop any write-ups. I drop 2 of your lowest web works, make a homework score out of that. That homework score is worth 15% of your grade. So that's like giveaway points. In web work, you can try a problem an infinite number of times until you get it right. If you get stuck, you can send me an email and I can help you do it. So your homework grade should be a nearly perfect grade at the end of the semester. Then the last part is a comprehensive departmental final. Every calculus student takes the same final exam on the same day. Your final exam is Friday, December 3rd at 10:30. All of your other exams are in our class, but your final exam is Friday, December 3rd. So when you're planning to go home for Christmas break, make sure you're here on that day. I don't care about the rest of your finals. I put your exams on September 20th, October 20th, and November 19th, probably because November 20th was a Saturday. I ain't working on Saturday. If I have to move those exams, then I'll let you know way in advance. We have a site called Blackboard on which I post handouts. Your syllabus is on there, course information, the suggested exercises are on there. And anytime we do a worksheet in class, it'll be on there. So always check the night before you come to class. They really don't want me printing materials and passing them out. So if you check on Blackboard the night before, it'll be something like, this is a handout we're going to do on Monday. Print it and bring it with you to class. I keep your grade book on Blackboard. There'll be recordings, like we're recording this one now, if you, by God, want to go through it again. But I post links to class recordings. I'm probably not going to record every single class because look how long that took me, and I had trained professional helping me. But I do have recordings from previous semesters. So if you ever miss a class, you can find a recording of the material. I also have PowerPoints on there from somebody else made them. I don't do PowerPoints, but there's a whole folder of PowerPoints for each section. There's how to do calculus. The whole thing is right there on Blackboard. My makeup policy is that the assignments, the web work, and the write-ups, I don't give makeups on those. I give you extensions if you need to take longer to do a homework. Sometimes you'll get to where you're really busy and then you thought, oh crap, I don't have time to finish web work. Just send me an email saying, can I have a few more days to do my web work? That's fine. The write-ups for each web work are due whenever you finish them. I like them to be the class meeting in which the web work was due. So if web work was due Monday night, bring them to me on Monday or Wednesday, I don't care. Or email them to me. But I'll take them almost any time. Just don't overwhelm me at the end of the semester with 15 different write-ups. So there's really no reason to miss any of that. Missed exam though, I put my makeups at the end of the semester. So if you miss an exam, let me know why with a note saying why. And I'll put them either on the last day of classes or on the study day, whichever works out best for you. And that keeps me from having to, excuse me, make a bunch of different exams. As far as absences, I know there might be times in which you need to isolate. So I understand that if you do need me to broadcast, if you let me know in time, I can Zoom while we have class and you can see everybody else having a good time and not you. No, but I understand. I do not want anybody to come to class if you're sick. Do not. I'm an old lady, don't try to kill me. So don't feel bad about missing class because we can handle it. We're ready to go online at the drop of a hat if we all have to take a break. So don't come to class sick. Then there's all this stuff that they made me put in here about the COVID pandemic information. The one thing I've got to say is that now you are college students and you can make up your own mind. If you feel that it is in your best interest to mask up, get a vaccination, let me tell you, I'm thinking the vaccines work. How many of you have ever had measles, chickenpox, mumps? Every kid my age had every one of those. But they don't exist anymore, or if they do exist, they're very infrequent and very minor because they have vaccines for them. And you all had these vaccines when you were an infant. And you had a booster right before you started kindergarten. You don't have to have measles, mumps, and chickenpox. I think this kind of thing is going to work here too. I trust doctors. You guys are going to be doctors, some of you. I think we have the best medical care in the world and the best researchers in the world. We're not going to glow in the dark. Spoons will not stick to our forehead. I think you'll be fine if you decide to go with the vaccine. And I encourage you to do it because you're living in a population that's very social. Me, I go nowhere. So I do encourage you. It's not a right thing or a wrong thing to do. It's part of the love one another thing to do. That's me. If I pissed anybody off, tough luck. It won't be the first time. Now, the next bit are the notes. If you have special accommodations that I need to know about, please let me know about them and I can take care of things like that. If you have to miss a class or a test because of a religious observance, that's excused. The last day to drop the class is November 23rd, which is right before finals. So if you're in a class that you're crashing and burning in, drop it. You get 6 drops in your college career. No reason to take a bad grade anywhere, especially if you're going to med school, right? If you're going to med school, the C is going to kill you. So when I'm talking to y'all, when I say bad grade, I'm not meaning a D or an F. I'm talking about something that hurts you. Those of you in engineering, C's don't get degrees. C in engineering makes you a math major. That's why I get all my math majors. So pay attention to your grades. I think it's okay to bring coffee, soft drinks in here, as long as you clean up after yourself, throw the stuff away. We have wipes up here if you need to disinfect before you sit down. I think we were the first class in here, I'm not sure. But you feel free to disinfect as you come in and go out. I want you to get to know each other. Most of you live around each other, or maybe you've had classes later on today. I went to an event the other night where 2 of my former Cal 1 students were there, and they're marrying each other. So look around, pick somebody out. Which is kind of cool. Feel free to talk in class, ask questions when you have questions. If I say something that makes no sense, point it out. If I go too fast, slow me down. If I go too slow, speed me up. Nobody's question is stupid, so don't roll your eyes when somebody asks a question, because I bet somebody else has the same question. How many of you have tried to log into WebWork? Does it go okay?
I had like 3 errors, but I finally got it. So
Okay.
it got figured out.
Okay, so the WebWork address doesn't have a www. So you just use that WebWork address as I've gotten there. If you've got the one online, you can just click on it. If you get into Blackboard, there's a link that takes you to WebWork. So you can just click on it there. And when you log in, your username is your same as your E-Rater name. Like when you log into your mail, but without the @ttu.edu. And your password is your R number with the capital R. So sometime today, see if you can log in. If you haven't used WebWork before, you enter things kind of the way you think you would. Like if your answer is the square root of 2, you don't need to get out the calculator and get, 8 decimal places for the square root of 2. WebWork itself is a calculator. You can just enter square root of 2. And you need parentheses only if you have things in here that are added, right? You can put something like that in there. It takes algebraic expressions. If you're putting an interval in there, if you want to enter this interval in there, then this symbol you write with the minus sign, and then you type the word infinity, or you can put INF. If you have disjoint intervals, you can use a union symbol, or you can use the word or sometimes it tells you to use a comma. So if you need to put something like this in here, right? What else about WebWork? Parentheses are free, no extra charge. So if it doesn't take your answer, you can see a preview. So if you want to put a denominator down here, you've got to put parentheses. Otherwise, it just takes the first term and uses it as the denominator. What else do I need to admit? You'll find it. If you find questions about WebWork, there's a button you can click on WebWork and it sends an email to me. And you can type your question there, or you can just send me an email and I can clear up WebWork. But it's a learn as you go kind of thing. Yeah, I can't think of anything else about WebWork. Can you think of any questions you want to ask me about the class? None. We used to do these 4 credit hour classes with 4 separate 1-hour classes, but now we've made them into 1 hour and 15 minutes. And this is the first semester we're doing that. So if I ever stop too soon, say, hey, we got more time. I got to stay here for the entire hour and 15 minutes. So we get out at 11:45. 7:45. Right? If you can't stand sitting that long and you need to sneak out, the bathrooms are right here to our right. You can just sneak in and out as you wish. Okay. Let's see if I got any questions here at home. Good? All good? Okay, let me see what you know about calculus.
Is this for a grade?
This is for a grade. Everything's for a grade. No, I just want to see what you know. What am I asking you to do right here? Take the derivative. All right, do it. Take the derivative. You remember this one?
No, I know that. Oh, wait.
It's been 3 years since I took it. Really? Yeah.
No. Who knows it?
I know what to do.
Tangent.
Secant tangent.
Secant tangent, that's what it is.
So secant of x cubed, tangent of x cubed. And then the chain rule gives us the derivative inside is 3x squared. Right? There's a list on Blackboard of derivatives that you should know. The 6 trig functions. This one. It's the derivative of e raised to the tangent of x.
E to the tangent x.
Good. And your chain rule gives us the derivative inside. Right? E to the x has as its derivative itself. Okay. Why do you need to know that?
Because it's important.
No, because when you go through graduation and you're an engineer, how many engineers in here? When the president shakes your hand, he's going to say, what's the derivative of e to the x? And if you don't know, he takes the diploma back. True story. Derivative of e to the x is e to the x. Okay. what about this little function here? Well, let me even kind of put a little bit more into it. You take the derivative of that. Too low for y'all? Let me see what you guys see back here.
Okay, so.
You're missing contact.
Right, okay, I remember the change, or the motion.
Done there, done that.
So,
Low behind
just,
my
So you're doing quotient rule, right? Quotient rule, bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom term squared. So in this example, the bottom is the polynomial. And now you're going to tell me what the derivative of the natural log of x is. Now minus the top. And now you're going to tell me the derivative of the bottom.
So x plus 2.
Cocky on that one, huh? All over the bottom squared.
are you good with this, just doing that and not?
Yeah, you can enter it just like that in WebWork.
Okay.
You don't have to simplify.
Could you enter it just like that in WebWork?
You can, it'll just give you a big red block. Something wrong. But what you can't do is this, right? You can't say, ooh, that looks like that one. Can't do that, right? Because of that. This dividing bar acts like parentheses, and the only thing you can cancel is a common factor, and that's not a common factor. So that would be a big old nope right there. Leave it just the way it was. Okay? We're not going to spend a whole lot of time simplifying, except for when we need to. I don't think we need to in Cal 2. Life's too short to simplify. Okay. Where have you seen this before?
Yeah.
That's the definition of the derivative of a function. Okay. Let's see if you remember this. Is that one? Or is that a question or a statement of fact?
I'm gonna go with statement.
Statement? It's one of the ones you can memorize. Or we've got a buddy named L'Hopital that says if you have the form of 0 divided by 0, and you take the derivative of the top divided by the derivative of the bottom, and then take the limit, what's the derivative of the sine of x? And then the derivative of x is just 1. So what's the cosine of 0?
1.
So this limit is 1. Okay. So where have you seen? What do we use the derivative for? Give me 3 uses of the derivative.
Slope.
Slope of the line that's tangent to the graph at a point, right? Because here's slope, change in y over the change in x. And then we make it real small, right? So that's how we determine slope. We drew a line through 2 points, then we squeeze those 2 points together with a limit, we got the slope at a point. Okay, so one application on a graph, the derivative gives us the slope.
Velocity?
It can be the velocity if our function represents position of an object moving along a number line or moving in the xy plane. First derivative of position is velocity, second derivative is acceleration. So velocity at any time t is the derivative of the position at time t. Acceleration at time t is the second derivative. of the position. What else can we use a derivative to tell us?
Rate of change, that's slope.
Any rate of change,
Yeah.
any rate of change, any instantaneous rate of change,
You can use it to find the extreme of. a function.
extreme values. We can tell where a function has a relative max or relative min. It's where the derivative is equal to 0. Those are our- Sorry?
Or undefined.
Or undefined if we have a sharp corner, right? All right, then here's another limit you may have seen. Let's see how you may have seen it. No, I don't want that one. I want, you write it.
What's the R thingy?
It's where? That's a K. K is my counter.
Gotcha.
Maybe I should do this at a particular point. What are we doing here?
Integration, is that summation?
We're taking a region in the XY plane from x is equal to A to x is equal to B. And we're making subintervals of with delta x. And making rectangles here. So this is delta, this is A plus delta x. This is A plus 2 times delta x and so on until we're out somewhere, we're at A plus k times delta x. And so we find the height of the function, that's that, times the width, that's that, and gives us that. And what does this tell me to do with it? Add them all up. And that makes them go out to here. That makes each of these guys. How did we write this? B minus A divided by N. We made N rectangles. Now we make N to be a big number so that these are real skinny. And then these little rectangles become line segments that color in and give us area under the curve. How else do we interpret area under the curve without the limit of a summation? It is a definite integral from x is A to x is B of our function. The height, that's the width. The summation symbol becomes the integral sign. So let me see if you remember how to integrate. We do all 4 of those. First one's a basic integral. What function has as its antiderivative, or what function has as its derivative 1 over x?
Natural log of x.
Natural log of x. So we put that in absolute value bar so that this 1 over x is defined for all x other than 0. Remember, you can't take the logs of negative numbers either. So we put it in absolute value bar so that they have the same domain. And then the arbitrary constant, which could mean things to us if we're doing total distance traveled and things like that. All right, the next one is a generic version of the one above. We've got a first degree factor in the denominator.
You have to split them apart.
Can't split apart the denominator,
Oh, yeah, you're right.
but we want to make this look like that. U substitution, we take u to be the denominator. Then we take the derivative of that. Right? And so I've got 1 over u. I don't have a 4 here, so I can move that over. And so this becomes 1 over u times 1/4 of du. Ooh, come on, 4. And that's just a constant, so I can pull it out front. And so I can write that as 1/4 times the integral of 1 over u du. Now it's that integral. So we get 1/4 times the natural log of the absolute value of u, where u is the 1 plus 4x. So I recognize that because I have a first degree factor, and that factor is raised to the first power. If I have something other than the first power, it's no longer a logarithm, but it is still a u substitution because the stuff in the parentheses is just a first degree term. But I'm going to do the same steps and write that as 1 over u squared times 1/4 du. How do you integrate 1 over u squared?
You treat as u to the -2.
And then you do the old add 1 to the power and divide by the new power, right? That's a power rule problem. So same steps. Gets you to here. Then we take the u squared and write it as u to the -2, and we do the power rule, which was add 1 to the power, divide by the new power. How far can I go over here? Keep going. So if I add 1 to a -2, I get a -1. And then I can put the negative with the constant. I can put the u back on the bottom. Like that. Right? Okay. Can't do that one with a substitution. Kind of. Right? Because if I take u to be 1 plus 4x squared, the derivative of 1 plus 4x squared is 8x, has an x on it. I can't pull out an x. I don't have an x waiting for me to suck that up. So I'm not able to do this one with a substitution, kinda. If that 4 weren't there, 1 over 1 plus x squared is an integral I know and love. Do you recognize that one?
Yes.
That's an arctangent integral. 1 over 1 plus x squared is the derivative of the arctangent of x. So we're going to put that 4 back and think of this integral as 1 plus 2x all squared. And we're going to make this look like the arctangent integral. So we put a little recall up here. The integral of 1 over 1 plus u squared du is the arctangent of u. The integral, the other inverse trig integrals we have of square root of 1 minus u squared du is the arc sine of u. And then finally, u square root of u squared minus 1 du, and that's the arc secant. of U. Those are the ones you probably forgot because that's about where calculus 1 left off, and we kind of went through that real fast, end of the semester stuff. So there's a reminder of those. And what we were going to do with the problem that I just erased, maybe?
Yes, 1/1
Plus
plus 4x squared.
All right, so let's put all the steps in that. I said I was going to treat the 4x squared as a quantity squared to remind me to use substitution. So I'm going to take the 2x and replace it with the variable u, and I'm going to replace the dx with 1/2 of du. Because if u is 2x, du is 2 times dx. So if I solve that for dx, I get that dx is 1/2 of du. And then I rewrite this integral as 1/1 plus u squared times the 1/2 du. But just like before, this 1/2 is a constant and it can come out front. Now it looks like my formula. So the integral there is the arctangent of u with the 1/2 tacked on in the front. And then u itself was 2x. So on Blackboard is a list of basic integrals that you should know. The power rule, we have 6 trig integrals. We have the 3 inverse trig integrals. Integral of 1/x was the natural log of x. Integral of e to the x was e to the x. I think that's all of them. So when you come upon one you've forgotten, maybe look it up or ask about it, and we'll do all the steps to it. We'll need to use a lot of trig to simplify some stuff. So there's a list of trig identities that we're going to need to use. Sum formulas, double angle formulas. We're going to use those. So make sure you can look those up. So it might be a good idea to print those things and kind of stick them in your notebook. So if you need them in class, you can just pull them out and look at them. We'll use them so many times at the end of the semester, you won't have to pull anything out and look at it. It'll all be right up in there. But I don't mind if you've forgotten things. So ask if I do something that you've forgotten. Okay, let's start. That was just the review. That's what you've done already. We had some theorems that had names. You already told me. Are you leaving me?
We're getting our notebooks out.
Oh, okay. I mean, you were just sitting there watching? Mean value theorem say. You might know the mean value theorem?
When you look at a continuous function from like 2 different points, there's going to be some point that's a slope of 2.
There you go. Mean value theorem essentially says on a closed interval, the continuous function attains its average slope, which is the slope of the line through the 2 endpoints. Somewhere in there, the slope of the tangent line is the same as the slope of the line through 2 endpoints. What other theorems did we have that had names? What's a fundamental theorem of calculus?
The integral of one point to another is just the integral, like when you actually like you do the integral.
And so you get something called an antiderivative, and then you evaluate the
that-
antiderivative.
From b minus a.
That's the fundamental theorem of calculus. It tells you how to compute a definite interval. Provided you got a nice continuous function. Think of anything else with names.
Roles.
Rolle's theorem is essentially the mean value theorem for functions that have the same endpoints. So I'm pretty mad at Rolle's for kind of putting his name on that theorem. That's really nothing new.
IDT.
Right? Mean value theorem says that if you have a function that passes through this point and this point, and it does wiggles in between, somewhere in there, the slope of the tangent line is equal to the slope of the line through the two endpoints. So here's what Rolle's stuck his name on. Oh, what if these 2 points were the same y value? Then that slope is going to be 0. So somewhere in there, the derivative is 0. Well, that's goofy. Why don't I just make a Schovanec theorem? Say the slope is 7. Somewhere in there, the derivative is going to be 7. And you can have whatever number you want.
Hi.
Hi. Okay, so section 6.1. We're going to look at the area, give me an A. Good gosh. That was hard to write. Area under a curve. Area between two curves. And we're going to look at area under a curve and between two curves as either a let's either do, this is vertical, that's horizontal. We're going to look at things that are vertically simple. Or we might look at things that are also horizontally simple. So we've done the things in Calculus 1 where you had a positive function. It's continuous over a closed interval. And we broke it up into n rectangles, found the height and the width, added them up, took the limit, and got that definite integral. And said that this area, so here's your typical rectangle with delta x. We picked some value of x here, say f of x k star. And we found the height of that one rectangle. And then we added them up. 1 or 0 didn't matter. And then we took the limit as n goes to infinity. We made a definite integral out of that. We can find the area under a curve as the definite integral. And it's under a positive curve, but above the x-axis. But who cares if it's not a positive curve? What if it's something like this? And I want to find the area from here to here. I can still cut this up into an infinite number of rectangles. Without a negative number, and I know area is not negative, right? Or I can just take this function and change its sign, flip it above, and now my area is positive. So I can say that this area here is going to be minus f of x, flip it around, dx from a to b, so that it's a positive number. Right? So this is f of x minus f of x is up here, and I have that same thing. If I bound this by another curve, whether both curves are up here or here, doesn't matter. I'll just draw them both up here. Let's say that this is y is equal to f of x. Put another guy here. y is equal to g of x, and I want to find the area in between these two. X is A to X is B.
Just
Subtract the,
lower one
Yeah.
from the.
Because if I'm doing this Riemann sum thing, and I'm gonna say, for instance, I want the left endpoints to give me the height for this rectangle that I've drawn here at, say, point xk. This segment is the y value here, which is f of xk, minus the y value here, g of xk. So that's the height, the width is xk. Apply that same Riemann sum. And then let n go to infinity. And that spits out a definite integral where the top graph minus the bottom graph is in here. But we've also seen that we can break that up into two integrals. If you so choose. Just find the area that's underneath. Y is equal to f of x, say from here to here. You can find all of that area with that integral. And then you can find the area underneath g of x with the second integral. And so to get the area in between, take all of that, subtract off that, and you got the area in between. So whether you write it like that or like two different integrals, that doesn't matter. But it does help to have a picture. Make sure you know which function's on top, which function's on the bottom. We're also going to have instances where sometimes maybe this function's on top, then they might intersect, and might be that this function becomes the top graph. So we need some picture to help guide us through our process. If we're able to draw rectangles where the top of every rectangle hits the same graph and the bottom of every rectangle hits the same graph, then that's what I mean by vertically simple. If the top of the rectangle hits a different graph, then it's no longer simple. And we might need to make it up into the sum of simple regions. So a picture guides us. That's some examples for you. So find the area. I can't see what crud. I got new contacts where I can see really well, one for each eye. But I can't see close anymore, at all. I mean, now I can. So I get to go to Walmart and get me my $5 glasses. And that's your job, is to always remember where I set my glasses. Because I'm going to ask you 5 times a class period, where's my glasses? Maybe just bring an extra pair for me. Okay, what kind of graph is y is equal to x squared plus x plus 1? All right. Find the area between, there's a between, how about that? Between that parabola and this parabola. Y is equal to 2x squared minus 1 from x is equal to 0 to x is equal to 1. Let's see if we can get a rough picture of these two parabolas. You knew they were parabolas because what? X is squared. So y is equal to x squared is a parabola that opens upward. These parabolas have been shifted somewhere. The absence of the first degree term in that second parabola means this one's just been shifted up or down the y-axis. Where's the vertex of this parabola?
-1.
At 0, -1, it's a parabola that opens up. So we'll draw that one first. Okay. That's y is equal to 2x squared minus 1. That parabola is crossing the x-axis twice. We'll take a wild stab at where it crosses the x-axis.
-1 and, or sorry,
Right,
I'm
one.
sorry.
Solve this equation right here. Y is 0 on the x-axis.
Plus or minus square root of 1/2.
Plus or minus square root of 1/2. Square root of 1/2 is the same as square root of 2/2. That's roughly 0.7, right? That might be pertinent. Okay, now the next parabola has been shifted left or right, I don't know. Would be nice if I knew where that vertex was.
Negative b over
At
2a.
one.
Minus b over 2a, if you remember that one, or calculus people where the derivative is 0. Right, the parabola that opens upward, the derivative of this is 2x plus 1. 2x plus 1 is equal to 0 when x is negative 1/2. So its vertex occurs when x is negative 1/2. When x is negative 1/2, y value is going to be 1/4 minus 1/2 plus 1. So it's at what? 3/4. So it's up. X is negative 1/2. I said square root of 2 is about 0.7. So it's going to be up here somewhere. And 3/4, if that's 1, I don't know. My scale's all screwy. It's going to be something, it's going to be up and open up, right? You know that it opens up. Somewhere they'll run into each other. I don't care. We're going to find the area from x is 0 to x is 1. Well, now I do need to know, do they intersect before or after 1? How do you find where two graphs intersect? Set them equal to one another. So let's find where they intersect. And x squared plus x plus 1, and find where it equals 2x squared minus 1. So let's just put everything on the right-hand side. So I'll have an x squared there, minus x, minus 2. Are there factors of -2 that add to -1? So they intersect when x is 2 and when x is -1. So that's pertinent. This occurs when x is 2, 4, 8. That's the ordered pair 2, 7. I don't care about -1 because I'm finding the area between x is 0 and x is 1. So that means x is 1 occurs before that point of intersection. So let's just put it here. So we're finding the area of this region right here. So now I want you to imagine that region cut up with an infinite number of rectangles. So I'm just going to draw line segments. When I draw these line segments in that shaded region, the top is always the parabola up there, and the bottom is always the parabola 2x squared minus 1. Agreed?
Yes.
So that makes it vertically simple. Every line segment that I draw in there vertically has the same top graph and the same bottom graph. So the plan is just find the integral of top graph minus bottom graph from this x to that x. And that should give me the area based upon making a Riemann sum. So it's vertically simple. And my glasses. So that's my plan. Get my area. It's going to be the integral of the top graph minus the bottom graph, both as functions of x. I labeled the bottom graph. I didn't label the top graph. It's the one that has the 3 terms. Bottom graph was the 2x squared minus 1. And then the a and the b are the vertical lines. X is 0 to x is 1. Correct? We can simplify that inside. I can take the parentheses away, collect like terms, and that'll give me less number crunching to do. So let me put these together. Minus x squared plus x.
Hold on, it's a plus.
Oh, this is a plus. And so that gives me them plus 2. Good? It's just a polynomial, so we can integrate term by term. So when I integrate minus x squared, what do I get? Okay. What about the x? And then the 2? 0 to 1. 1 goes in first, and then the 0. 1 to any power is 1, so I get minus 1/3 plus 1/2 plus 2. Then when I put a 0 here, all of these 0 out. I want to make sure my area is positive. That would reaffirm what I did wrong, or if I did anything wrong. You can leave your answers here. You can enter them just like this in the web work. But I'm going to do it because I'm a trained professional. I don't always do numbers. It's in my contract that I don't have to. Common denominator is 6. I have -2/6 plus 3/6 gives me 1/6 plus 2. So I get 2 and 1/6. I want to enter a mixed fraction, so that's 13/6. It's a nice positive number. So I'm going to believe that that's the area. But again, you could stop right here.
Would you like us to have units squared or anything?
Yeah, I don't care about units. Eventually, when we get into doing work, we need the work units so that we know whether or not we're using the right gravitational constant area square units. Now, I probably could have done this one without the picture, but the picture does play a role because what if then I had said do the same problem, but now let's integrate, say, from x is 0 to x is 4. And we found out that they intersect when x is 2. So what happens between 2 and 4?
The top one's on the bottom, the bottom one's.
That's right, they change position. So out here, I gotta write a separate integral to integrate from 2 to 4 with these guys swapped. If I just try to go from 0 to 4, I'm not gonna get the right answer. Because you'll be adding a bunch of negative numbers to a bunch of positive numbers and get gibberish. So you have to pay attention to what the region looks like in the XY plane. So if you have something that crosses itself, here's y is equal to f of x. And here's y is equal to g of x. And we want to integrate from x is equal to a to x is equal to b. And there's some point intersection at x is equal to c. Then we have to pay attention to what's on top. And so our area would be the sum of 2 integrals from a to c. I've got f of x on top and g of x on the bottom. Oops, that should go here. And then from c to b, it switches. So I got the g of x on top. Okay, so these would be the sum of vertically simple regions. It changes once we cross that point of intersection. So pay attention, the picture is going to help you out. And it could change several times. If there's symmetry, if this region is the same size of that region, I can just do half the problem and double it, right?
Yeah.
So use symmetry, it's your friend. Let me see if I got one that does that. Draw me the graph of y is equal to the cosine of x. And we want to find the area underneath the graph of y is equal to cosine of x and the x-axis from x is equal to 0 to x is equal to 3 pi over 2. Find the area between y is equal to the cosine of x and the x-axis from x is equal to 0 to x is equal to 3 pi over 2. All right, so let's see. One of our trig functions looks like that through one period. One of them looks like that through one period. Which one's on the top? Top one is the sine graph. The bottom one is the cosine. So y is equal to the cosine of x does that through one period. One period is a length of 2 pi. So it starts up here, 0, 1. Comes down, ends back up at 2 pi 1. Halfway in between, it hits a minimum. So halfway between 0 and 2 pi is pi. So this point here is the ordered pair pi negative 1. So halfway between 0 and pi, this bad boy crosses the x-axis. Halfway between 0 and pi is pi halves. And so this one over here is 3 pi halves. And so we want the area between the cosine graph and the x-axis from here to here. So if I shade it, we want the area in that bit and then in that bit. Agreed? Well, that's not vertically simple because in here, vertical rectangles touch the cosine graph on top, the x-axis on the bottom. But once I cross that point of intersection, it touches the x-axis on top and the cosine graph on the bottom. So I'm going to do this with two integrals, right?
You can do one in just the first
-2.
nub, yeah.
What do you mean?
The area on the bottom should be double what's on the top.
Yeah.
So
This area is double that?
Yes.
I agree to that.
You
So
just do 3 times the first nub.
3 times this first nub,
Yeah.
put that one in that one, that would work. That would work. I'm just going to do 2 separate integrals. I'm going to integrate from 0 to pi halves. Put the cosine of x in there. And then I'm going to integrate from pi halves to 3 pi halves. And what's going to go in my integral? Negative cosine of x, right? Because that agrees with what we said here. What's the equation of the x-axis? Y is equal to 0. So here I'd have 0 minus cosine of x. So while you're writing these integrals, see if you can remember what the integral of the cosine of x is. Who remembers?
Let me.
Negative sign of x.
negative sign.
Negative sign?
That's just
It's just a sine.
That's
Oh, wait, it's
just.
nice.
Okay, what's the derivative of the sine?
Cosine.
So what's the integral of the cosine?
Sine.
We go back and forth. So the integral of cosine is the sine. So here I get the sine of x, and I need to evaluate that here. Here I've got this minus sign, so I'm gonna put it there. And then I get the sine of x here from pi halves to 3 pi halves. And so what we need is the sine of pi halves minus the sine of 0. That's this. Now that minus sign is that one. Now I need the sine of 3 pi halves minus the sine of pi halves. So now let's think about our unit circle. Can you see your unit circle? Unit circle is the circle x squared plus y squared is 1. An angle of measure 0 corresponds to the positive x-axis. The angle of measure pi corresponds to the negative x-axis. Pi halves is the positive y-axis. On the unit circle, 3 pi halves is the negative y-axis. And our ordered pairs there are 1, 0, 0, 1, negative 1, 0, 0, negative 1. The sign is describing which member of the ordered pair, x or y. Y value. So what's the sign of pi halves?
1,
Good. The sign of 0?
0,
Good. Sign of 3 pi halves?
-1.
And then back again to sign of pi halves. So I have 1 minus 0 minus a negative 2. So I get a total area of 3. Isn't that amazing how a transcendental function can enclose an area that's a nice whole number? Okay, now I want you to give me these two graphs. Y is equal to x squared plus 1, and y is equal to 2x plus 4. Those two graphs enclose an area. X squared plus 1 is your first y value. 2x plus 4 is the second one. Find the area enclosed by those two graphs. Describe for me y is equal to x squared plus 1.
The parabola moved up 1.
Parabola moved up 1. So the vertex at 0, 1. What about 2x plus 4? Line with a slope of 2. So it's probably going to put the top on that parabola. Parabola with a line going across the top. Right? Here's y is equal to x squared plus 1. This is the ordered pair 0, 1. This has a y-intercept of 4. So let me put this as 4. And then a slope of 2. And so they intersect there and there. So the area between them is this bit right here. So now imagine that region cut up with an infinite number of vertical rectangles. Will every single vertical rectangle hit the same graph on top and the same graph on the bottom? So it is vertically simple. So we're going to integrate top graph minus bottom graph from where to where?
Negative 1 to 3.
Because
That's where they intersect.
find the point of intersection. You're saying -1 to 3, let's do that on paper. Set the two equations equal to one another. and see if you can find those 2 points of intersection. Let's see, it's a second degree equation. We need a 0 on one side. And then I combine like terms. I can write that as x squared minus 2x minus 3 is 0. And factors of -3, opposite in sign to give us a -2 in the middle, would indeed be x minus 3, x plus 1. Now you set each factor equal to 0 to get the x is 3 and the x is -1. So that completes our picture. Again, always eyeball it to make sure rectangles will always hit the same graph on top, same one on the bottom. And then our plan is to integrate top graph minus bottom graph from lower leftmost x to rightmost x. So leftmost x was -1, rightmost x was 3. The top graph is the line. Bottom graph is the parabola. We can simplify and then integrate. And when we simplify, we can write that as minus x squared plus 2x plus 3. Do the power rule down the row. So negative x to the third over 3. This will be 2x squared over 2, so the 2's will cancel. That's a 3x. Agree to that? Did I do that part too fast for anybody?
I have a question.
Yes, ma'am.
So, I guess on the top step right there, yes, no, right, yeah. So instead of distributing the negative sign,
You can
you,
just integrate?
yeah.
Yeah.
So you just combine the like terms though.
Yeah,
So-
well, because there's nothing else I could do.
Well,
Right.
I mean, my head wants me to distribute the negative and make it negative x squared and -1.
And I did, and then I took the -1 and put it with the 4.
Oh, I'm stupid.
It's just morning.
Yeah.
It's almost morning. Right, this is when you guys normally wake up?
Usually.
Usually.
Without my alarm, I was up at 6.
You were excited, weren't
I was, it was for school. My lunchbox packed, kissed my mom goodbye. My mother used to always make me egg salad sandwiches, which I love, but when you open that locker at noon. Okay, so I'm evaluating this between -1 and 3. Well, let's do it. I'm going to put a 3 in for each x. The minus sign comes last. So 3 cubed is 27. 27 divided by 3 is 9. So I'm getting a -9 right there. 3 squared here is 9, so that adds to 0. 3 times 3 is 27.
9.
Oops, 3 times 3 is 9.
I was very scared for a second.
Always remember that I'm the one who computes your grade. Minus -1 to any power is -1. That other negative makes it +1. -1 squared is 1. And then I get a -3 on the end. So I probably would stop here.
Is it -1/3?
No,
Oh, yeah,
because
because.
this will be
it's-
negative, and then with that negative makes it positive. So I probably would stop there since we're out of time-ish. Okay, what we did today, we did this way. That's vertically simple. Sometimes we'll be able to do it that way. We'll look at horizontally simple regions. If we do that, then the thickness of our rectangle is a dy. And so we specific functions of y here with a dy. and read up and down. All right, so we're about halfway through section 6.1.
Is there a work assignment over this for today?
I don't remember if I put one or not.
Okay.
The web work I'll give you about a week to do. So I'm not sure if I put one up there or not, I may have. But try to log in and let me know if you have any trouble logging into the web work.
Oh.
If not, I guess it's good.